So welcome to this video. We are going to do some revision about design of some calculations about the design of retaining walls. Okay, and so some questions for revision. So the first question is calculate the minimum depth of embedment D to provide stability to cantilever sheet pile while retaining an excavated depth of 6 meters using the properties are shown. So phi peak is 30 degrees, C naught is 0, and gamma is 20. So this is so there are two ways of doing this, the BS8002. So BS8002 procedure demands of us that we apply as a charge of 10 kilonewton, as you can see, and provide 10% of the clear height for future excavation. So having done that, and also we apply a factor to design phi. So design phi, to the given phi, sorry. So design phi is tan inverse of tan phi divided by 1.2. So if we do that, we get a value of 25.7 degrees. Okay, and then this now is the value we used to determine Ka. Okay, Ka now tan squared 45 minus 25.7 divided by 2. We get 0.395, and Kp is the inverse of Ka, or you can use tan squared 45 plus 5 over 2. We get 2.57. Okay, so those are the first two things you need to calculate, and then now you can make the simplified stress distribution. You can do the simplified stress distribution profile. And so so often we say so so it's first crucial to know how to determine. So this value is 0.395 a little bit difficult to know to write, times 20 times the height, which is 6.6 plus d naught. Okay, so basically that's what this value is. Okay, so it's already written there. So this is the value at the bottom. Okay, so this is how to calculate the so this is how to calculate that length there. Okay, and then the area we know, so you can simplify, as you can see with this, and you know that the area to get the PA1 is simply the area. So this is the area of the stress distribution diagram. Okay, which is a half times base times height. So a half, you can see, so this is the base times the height. Okay, and this is a matter of algebra. So this is the how to derive this equation, the formula. The rest you can do and solve. And like I said, this no one is. I hope it's correct. I double checked, but you can also check from your calculations and see whether you get that expression. Okay, so this is the area, and then the moment is again the value PA1 times the distance, which is 6.6 plus d naught over 3. Okay, so that's what we're trying to do here. So PA1 is this, and then the distance. Okay, and then that is just algebra again. You can do and simplify. Okay, this is what I get. You can check the answer again if your yes agrees with this. Of course, depending on the number, the way you round off, there might be some slight difference, but the equation should be in one way or another that form. Okay, and so now because we already have dealt with this, so it's easier to proceed to this, so that we you can connect the dots. So this one, that value is kp. Kp is 2 point I think 53 times gamma is 20 and times d, so times d. Okay, and then the area is half, okay, the base, and then times height, which is d. Okay, so that's the force, and then times the central distance to the center, which is d naught over 3. So should be fairly straightforward. Okay, so that's what we have done here. Okay, yes, so this is what we have done here. So I've skipped because the passive and the active side are all triangular distribution, so it's easier to connect. Okay, and then when we check now, we go to this other distribution. So this is the surcharge is just a rectangular distribution. So rectangular distribution, the area of that is 10 times 6.6 plus d naught, yes, d naught. So that's the area, but don't forget to multiply by the coefficient of lateral earth pressure, which is 0.95. So that would be the force, but now times the distance to the center is 6.6 over 2, so that becomes squared, and this is divided by 2, so that's the moment. Okay, so you have an expression for the moment. This is from the passive, this is from the active side, this is from the passive side, and this is what I've just demonstrated you. This is also on the active side, but this is due to the the surcharge. Okay, and then now depending on your sign convention, so if you take the moments here, this will try to rotate this thing anti-clockwise, and this will try to rotate it clockwise, and similarly this will try to rotate it anti-clockwise. So if you decide whichever value you decide to be negative, I don't know which one, but in this case I think it's easier. Okay, let's say the anti-clockwise ones are positive and these ones are negative. Okay, so so then all we will say that the summation of moments at point O is 0. Okay, and then we try to add these expressions based this one and this one and this based on the sign convention. Okay, and we've said this is negative, so that means these ones are positive and these ones are positive. So that's the equation we get here. Okay, some algebra, but you find a way to solve. At the end of the day, you need to end up with an equation like this. So okay, so once you end up with an equation like this, you have the bulk of the marks, because you can see from here the rest you can get only about 1.5. So you have gotten the bulk of the marks at this stage. So this is just an algebraic equation which you can solve in using whatever means. The first, what people can do with manually is usually to write the left hand side, so left hand side, and then the right hand side, so through some trial and error. But here you have to make an educated guess, because so you say, for example, the left hand side, say d naught is the value of d naught is 1. You substitute 1 in this formula, the right hand side has to be 0 or a value close to 0. You see what value it is, you choose 2, see what value it is, 3, and so on. This is just the way it is done, but you need to think a little bit, because if you choose 1 here and you see the value is different, the right hand side is not 0, then you can realize whether you need to increase the value or increase the value. It will help you decide by how much you can adjust from the value of 1. Okay, and when the right hand side is closer to 0, that means the value on the left hand side is more or less the right value. So that's one way to do it. Another way is you can use if you in a non-programmable calculator. Of course, I'm talking about an exam scenario. Non-programmable calculator, for example, FX992, you can be able to plug in something like this and give you an answer. Okay, so this is in the case of an exam. As long as it's non-programmable, you're good to go. Okay, but in practice, of course, you are free to solve this using any means that you can solve. Another option is the ChatGPT, but I have to caution you, ChatGPT, in my experience, it doesn't give correct answers often. If for example, if you type this, it will give some values that are not correct. If you point that out, maybe it will recalculate, and that's maybe that time it can give you the correct value. So you be cautious with that. But I think keep it simple. Calculator should be able to solve, or you can put this in an Excel or indeed any algorithm that is able to solve. You can do you program a simple program that should be able to solve this fairly easily. Okay. Anyway, whatever means you solve. So this one, get did not to be 8.19. There are negative values which you don't need because they don't make sense, so you choose the positive value. And then D is 1.2 denote, and then you can see the solution you end up with. And also you can also see the distribution of the marks as will be awarded. Okay, so that's the this BS8002 method. So note, BS8002 method, you provide 10% of the clear excavation depth for future expansion. Okay, and also provide us a charge of 10 kilonewton per meters, and that is realistic, because when you'll be working, there will be machines will be being we will be using machines here. Machines will be used at this to help you do the excavation. So the surcharge is a very reasonable addition. Okay, so that's the BS8002. Then the CP2 method, the only thing is we need to apply a factor of safety of 2 on the passive side. We don't need the provision of 10%, so you can read. So here, phi was 30, you use it the way it is, so tan squared 45 minus phi over 2. That gives you a third, and Kp is the inverse of a third, which is 3, or tan squared 45 plus phi over 2. Okay, and then using the same logic that we have done before. So here at the bottom here, Ka is a third, so that would be a third times 20, and there we don't have any provision for future excavations. This is just 6 plus denote. Okay, 6 plus denote. Okay, and then the area now would be a half, so you put 2 here, a half, base times height. Height is 6 plus denote, so denote. Okay, and then to get the moment is 6 plus denote over 3, so this is cubed over 3. Okay, and that's what we're trying to do here. Okay, and then you can simplify, so up to the moment. Okay, so that's what you end up with. Now this is the force, and this is how to get the moment, and then you end up with an equation like this. Okay, and more or less on the other side should be even easier, because here there is the issue of surcharge is not there, so we don't have this part. Okay, So we only have this, and that is Kp. Kp is 2.53 times 20, okay, times d. Then to find the area is a half base times d squared, okay, and to find the moment is d times d over 3, so d cubed over 3. Okay, this gives you about 8.43 d not cubed. But don't forget to divide by, no, is it 8.43? No, this is not, I'm sorry, this is not 2 point, this, the Kp now is here is 3. Okay, so this will cancel out, and that gives you 10d cubed. Okay, 10d cubed by a factor of safety of 2 will give you 5d cubed. Okay, so this is, should be, is fairly straightforward, and if you follow the logic, so that's how we end up here. Okay, then you decide which one you want to be positive. I don't know what I did here, so this is negative and this is positive. Okay, so this is positive. Okay, so you combine them and end up with some equation there. Okay, whichever way you decide. You can also actually choose the reverse, that the clockwise are positive, the anti-clockwise are negative, or anti-clockwise is negative, is positive, and clockwise are negative. As long as you do it consistently, you're fine. Again, this is an algebra which you can solve using a calculator, ChatGPT, and so on. Okay, and the so again you solve d naught as 9.22, and then find d as 1.2 times d naught, which is 11.06. And notice the differences. The notice the differences between the, when we use the CP2 method and the CP2 method, and also the BS800. Of course, it appears BS8002 method is a bit more rigorous. Okay, a little bit more rigorous, but the CP2 method is simpler. But you overestimate a little bit, but it's okay. Your structure would still be safe nonetheless, and you can see the computational effort is a little bit less in comparison to the more rigorous. So the issue, if we are not rigorous, we overestimate a little bit, but at the end result is your structure is safe nonetheless. But if you the more rigorous method, you can see the calculation is the calculation is more rigorous, and then we get figures that are a little bit more economical. Okay, and so the question 2 is how is designing a retaining wall, is to design a retaining wall. And so using the BS8002 or Eurocode 7 guidelines, find the factor of safety of the wall shown against sliding, and the limit is 1.5, overturning, and the value is 1.5. The bearing capacity and the factor of safety against bearing capacity is 3. And so the given the allowable bearing capacity is 200. Take C is, I think this is an error, because in my solution I've assumed C to be 5 kilonewton per meter squared per meter. So that correction, this should be 5. Okay, and 5 is 32. 5 prime. Comment on the calculated factors of safety. Given this is 19.5. Okay, so ignore passive resistance, and one hint, because this height is not given. For you to calculate passive resistance, you need that height. So if it's not given, ignore it. Of course, if you're told to include it, you have no choice but to include it. But now you can ignore it, and this is often what we do. We can ignore it to have conservative design. Okay, so having said that, according to BS, we have been specifically told to use BS 8002. So BS 8002, we provide a design, we calculate a design phi using a factor of 1.2. So and then given this is 32, so this gives a value of 27.5. That gives Ka as 0.368. So should be easy because so at the bottom here, calculating this value would be 0.3. Is it the value is 0.368? Okay, 0.368 times 20 times 5. Okay, so again, if you want to find the area or the force is a half, this is the base times the height, so that makes this squared. Okay, so it should be very easy. If you want to find the moment, you multiply this value by a 5/3, but for now we only want to find the force, so this is about 89.75, I believe, 0.75. Okay, and then the distribution due to the surcharge, so this is 10 and this is 5, so due to surcharge is just 10 times 5, but please don't forget to multiply with the coefficient of lateral earth pressure, which is 0.368. This gives a value of about 14.5. Okay, 14. Okay, I don't know, 0.5 or 0.8 kilonewtons. Okay, so in terms of so I did not draw an illustrations, but in terms of an illustration, so this force here, so this is the 89. Okay, about 89, and then this force here is 14. So all these forces are trying about 15, let's say. So if you are talking about sliding forces, you add the two sliding forces. So those are the this is what consists of the sliding forces. So 89 plus 15. So this is what we are doing here. Is an estimation, so not exactly. So 89.75 plus 18.4. So those are the total of the sliding forces. Now the issue with the so this is what makes the difference between okay, this is what differentiates, or what where we have a difference when we are talking about the ABS 8002 method. So the effective would be C. Okay, C plus RV. Okay, RV tan delta. Okay, so this delta is the design phi. So in this case, we'd say tan. Okay, this one we already found to be 27.5. Okay, 27.5, and the C is 5 kilonewton per meter. So this will be confusing, but it was 5. So this would be to get for the entire length of this would be times 3. Okay, but in terms of the BS 8002 procedure, you have to multiply this by 0.75. Okay, so we modify it a little bit. So this is BS 8002 method, strictly speaking, but normally what we do, we just say C is 2/3 of the C. Okay, and delta is 2/3 of phi. So usually that is okay. So if you are not told which method to use, you can use the BS 8002 method. You can use this other method. Okay, so in this case we are told to use specifically that method. Okay, but the idea is that this phi, C, and C must be modified a little bit to cater for what happens in reality. Okay, so after you do that, you multiply by a factor of 0.75. But before then, you have to find what RV is. RV is simply this the weight of this, or the weight of part A, okay, weight of part B, okay, weight of part C, okay, and the contribution to the surcharge. Okay, so this would be, for example, weight of part A would be 0.4 times 4.6 times the unit weight of concrete is 24, isn't it? So while I'm here, it's easier to explain. And then if you want to find the moment, it would be the centroid there. So this value would be 0.7. So the moment would be that times 0.7. So similarly, for part B, the area would be 3 times 0.4. Not the area, but the force 24. But the moment, so if we get to the moment, would be the distance is 1.5, okay, times 1.5. So this is just to make sure we are understanding. So now the weight of the first part, you can see the weight of this part B, the weight of the part with the soil. So remember the weight, this is soil, so the unit weight is different, okay, the unit weight is different. So that's the DSO 19.5. And of course this is a UDL, the effect of UDL W times L, which is in that case 10 times. This distance is 2.1, okay, 2.1, okay. So so that gives you 282, okay. So that's the only thing that was missing in this formula. We can substitute and get 128.48, okay. And so so this is the resisting force and the sliding force. So factor of safety against sliding is resisting forces over sliding forces, which is 121.4 is it 348 divided by 108, and is 1.12, less than 1.5. So this is not okay, okay. So but I've seen that if C were 0, the way we said here, so we'd move this part, and this would be about 110 point, I don't know, 0.22 or something like this. Then the factor of safety would in fact would be even be less. So this would not even be still not be okay. It would be 110 divided by 108 or thereabout, 108.15. So this value would be about 1.01. The value would be about 1, which is still not okay, okay. And then the issue about overturning now, the forces, so to find the factor of safety against overturning is fairly straightforward. So this one was 89, right? 89 about, or 89.75. Because it's a triangular distribution, we assume this value is 5/3. So 89, for that is 89.75 times 5/3, okay. And for this one, the value here was about 1415, and then the distance here is 5/2, and this was 14, I think, 0.8, if I'm not wrong. So this would be 14.8 times 5/2, and then you add the two. So those are the driving moments. So this is what we have done here, that plus that, okay. And then this other one, I think I already explained, but it doesn't hurt to explain once more. So like for this distance is 0.7. So the area, if you calculate the force there, that would be 28.8, then times 0.7. That's the first part. And you can do the same for this part, whose center is the distance to the center is 1.5, okay. and these other ones, the distance to, I think, is 1.95 for all of them. Okay, and also something I needed to explain is that what did I want to say? Oh, yeah, okay, the moment, the place where we're taking moments is point A, but actually you can take even here, as long as you're consistent. So the distance will change a little bit, but even if you take from here, it should be fine. Okay, so the moment, so 28, I think there's some error there. Okay, yeah, so this is for the B, the part B. Okay, and this is the part A, and this is from the soil, and this is the due to the UDL. Okay, so it should be fairly straightforward. So just to be clear, so this is part B, and this is part A. So it's just geometry, and this is the contribution of the soil. No, there the soil starts there. Okay, and for the UDL, so it should be easy. So then you add, and this gets 48. You get 482.42. So those are the resisting moments. Then the factor of safety is resisting moments over the driving moments, which is 482.4 over 195. So also note there is an error here. The limit we were given was 1.5. So that this is okay. This value, that calculation is okay. Okay, and the bearing capacity. This equation actually comes from this sigma v equals, you can revise your own mechanics, so plus or minus mx, okay, over I yy, okay, or plus or minus my y over I x, and you can prove this from mechanics very easily. So you use b over 2 minus the differences in the moments, then you get eccentricity of 0.85, and you have to check that the eccentricity is less than b over 6, so that means we don't have tensile stresses, so we are fine. Then you use this formula to get the maximum. We are ignore, so here we just concentrate on the plus side, because the one where we are subtracting, we are interested in the minimum, but if the minimum is not tensile, then we are fine. Okay, so, and we've confirmed that. Okay, so now we just look for the maximum. So we substitute the E we have been calculated from there, and then the rest of those you already know, and we get 185.38. Okay, then the factor of safety is the bearing capacity over maximum applied stress, which is 185 in this case, or 200 over 185.38, 1.08 less than 3, which is not okay. Okay, so these are very simplified way of finding eccentricity, and we can prove where that equation comes from your materials. Okay, so finally, consider a pile with flat driving point having an outside diameter 457. The embedded length of the pile in layered saturated soil is 20 meters. The following are the details of the subsoil. So here, no friction has been mentioned. So in this case, it appears that this is an end-bearing pile, because the information that is given to you will also point to you on how then you are supposed to solve the problem. Okay, so this is already in the was in the notes. So just to remind you where probably you can get this or an idea or read more. Uh, yes, so where you can read this in the notes precisely So where is this now? I think bearing capacity of deep foundation. Yeah. So here, all this. So just to start to show the solution. So the first one, so you refer to class notes where we derive this. So QP is 9 CUAP, and so you can go and follow how we reach there. So this is Mayhoff, so that's for sand, but we're looking for clay. Yes, so remember this. So this is for saturated clay, so 9 Cu, and here because we are assuming phi is 0, if you check the bearing capacity factor, then C is about 9 or thereabout. Okay, for deep foundation. Okay, so that's how we got 9, and Cu, we are told the end is at 20, so 20 is here, that means Cu is 90, and the rest of the things are just geometry. So pi 457, I get 132.9. Okay, then using Vesic's method, again you need to follow a little bit from the I'm showing the notes for the benefit of maybe other readers, but of course, to understand this completely, you need to have some idea or some background information. So if you have some background information, what I'm showing you is just to help you so that you know where you can find more information. So on the Vesic's method, so this is sand, but we are talking about clay. So for clay, on the Vesic's method, yeah, for clay, for Vesic, again, this is the idea. I don't know where my cursor has disappeared to. Let's see. My cursor has disappeared. Let me look for it. I don't know why. Control Z. Save. I don't know why my cursor seems to have disappeared. Yeah, so just to explain, so this is for unfamiliar readers unfamiliar with this, or viewers unfamiliar with the but of course, to understand completely, you need some background information. So this is the basic formula which you have seen as used, and there's some bases there also. Okay, it has disappeared again. That for saturated soil, IRR is the same as IR. Okay, so and then IR can be calculated ES over 3 CU. Okay, and ES have we been given? Yes, and IRR can be found by 347 Cu over the so ES actually can be found if you read the notes. Yes, this is IR, right? Okay, so IR is the same as so, and then you come to this table. The so let's see the so based on IR you get 279.3, and then you come to this table. 279 is somewhere here, so the values are between 10.97 and 11.51. So if you extrapolate from that table, you get a value of 11.4, then substitute in this formula, get 168.3, and in such a scenario you get two different values, you find the average. Okay, so just to demonstrate how to use this, The rest you can, if you don't know where to. So for unfamiliar readers or unfamiliar viewers, you need some basic information, but you can find more information in what, like I have tried to explain. And if you are looking really for more information, go to any or advanced foundation by any advanced foundation book. You should be able to find more information. Okay, so thank you very much. This was meant for my class, but also for other viewers who may benefit. Why not? Okay, so thank you very much. I see you next time for my other videos.